The previous video looked at the background for conducting hypothesis tests for a population standard deviation, and in this video we'll take a look at an example of how you would conduct this kind of a hypothesis test. Our first example is similar to section 10.4, exercises 9 to 14. Optical Solutions is a scientific equipment company that produces lenses for optical telescopes. Last year, the standard deviation of the thickness of their lenses was 4.25 millimeters. This year, in an effort to lower the standard deviation of the thickness of their lenses, engineers at Optical Solutions developed a new technique to sculpt the lenses. After implementing this new technique, the engineers obtained a random sample of 20 lenses and measured the thickness in millimeters of each lens. Here are the results. So here are the results of their measurements on those lenses. Is there sufficient evidence to conclude that the new sculpting technique was effective in lowering the standard deviation of the thickness of the lenses? Use an alpha of 0.05 level of significance. Also note that a normal probability plot and a box plot indicate that the thickness of the lenses are normally distributed. So I want to note a few things in this problem. They are talking about how last year the standard deviation was 4.25 millimeters, and then this year they're trying to lower the standard deviation, and so they have this new sculpting technique, and to see if that new sculpting technique is working, they obtained a sample of 20 lenses. There's the N, and then these were the results of that sample. We'll also want to make a note that in the question they state that is there evidence to show that this new sculpting technique was effective in lowering the standard deviation. So that keyword lowering, and it's the same word that was used up here, that's going to affect how we write the alternative hypothesis. So again, step 0 is going to summarize the information and just identify any point estimates. So again, to summarize, we're comparing last year to this year. Last year, the standard deviation was 4.25 millimeters. This year, they're introducing this new sculpting technique, and to see if it's working, they get a sample of 20 lenses, and they measured the thickness of those lenses, and then they came up with these results, and ultimately we'll have to calculate the sample standard deviation, which is our point estimate. And to calculate that from these numbers, you can either use a formula or you can use a calculator. And for now, I'm going to mostly emphasize using a calculator, but you could use the formula to work this out. So using a calculator, you could take these steps on the Casio calculator, or if you have a TI calculator, you could take these steps to calculate the sample standard deviation. But either way, when you do that calculation, you'll get a sample standard deviation of 3.13 millimeters. So that sample standard deviation of the thickness of the lenses, 3.13 millimeters, is lower than the standard deviation of the lens thickness using the old technique, which was 4.25 millimeters. And so this seems to indicate that perhaps the new technique has reduced the standard deviation of the lens thickness. However, we'll need to test whether the sample standard deviation of lens thickness using the new technique, so this amount, is significantly lower and therefore sufficient to conclude that the population standard deviation of lens thickness really has been reduced. Step 1 is to state the hypotheses, both the null and the alternative. This hypothesis is involving a population standard deviation, so we'll use sigma to represent the population standard deviation, and in particular, sigma represents what is unknown in this hypothesis test. And the unknown is the actual population standard deviation of the thickness of lenses produced using this new sculpting technique. So it's known that last year with the old technique, the population standard deviation was 4.25, but what's not known is what's the standard deviation for this year, and that will be what sigma represents. And here are the hypotheses. The null hypothesis is always going to have an equal to here, and so this is saying the standard deviation under the new sculpting technique is just the same as the standard deviation under the old sculpting technique, which was 4.25. The alternative hypothesis has this less than symbol. Remember that in the wording of the problem, it used the word lowering or lower than. And so lower indicates less than. So the alternative hypothesis is saying the standard deviation with the new sculpting technique is less than the standard deviation under the old sculpting technique. And again, on quizzes, homeworks, on the final, and in your own research, you would usually write your hypotheses in these symbols. But in the lecture notes, I went ahead and wrote the full sentences out just to give full clarity as to the meaning of these two hypotheses symbols. Alright, we'll go on to step 2. Step 2 is to verify the requirements for this hypothesis test. There are only 2 requirements for this particular test. The first requirement is that the sample must be a random sample. And the second requirement is that the population from which the sample is drawn must be normally distributed. Let's check these requirements. The first requirement, the sample must be a random sample. Well, in the description they do mention that the engineers obtained a random sample. So it mentions that in the description, and that will satisfy that requirement. The second requirement, that our population must be normally distributed. Well, also in the description of the study, they mention at the end that a normal probability plot and box plot indicate that the thickness of the lenses are normally distributed. So they mention in that description that they check that and it is normally distributed. If you were doing this research on your own, you would have to really check this. In our class, we don't emphasize normal probability plots, but in your own research, you would need to know how to do this and check this and make sure that your sample data is normally distributed. Alright, we'll move on to step 3. So step 3 is to test the hypothesis. And there are 2 and sometimes 3 ways to test these kinds of hypotheses. Again, you won't have to know all 2 or 3 approaches on a quiz or test or homework. You can use any one of these approaches. So one method or one approach is the classical or the test statistic approach. And so with this approach, the first thing that you'd want to do is sketch the chi-square distribution probability curve, and then use table 8, another table, to determine the cutoff value, which is chi-squared 1 minus alpha, for the region of the curve that will represent unusual or significant study outcomes. So according to our question and our alternative hypothesis, this is a left-tailed test. Also, we'll want to note that alpha is 0.05, and that's the area under the left tail of the curve. And so the chi-square distribution will look something like this. This is a left tail test. Here is the cutoff chi-squared value, and alpha of 0.05, that's the area of that left tail. Now we can go to Table 8, the chi-square distribution table, and use that to look for that critical cutoff value for the left tail of our test. To use Table 8, you need two pieces of information. Number one, you need the degrees of freedom, and number two, you need the area under the curve to the right of your critical chi-squared value. The degrees of freedom is n minus 1. Our sample size was 20, so that's 20 minus 1, so 19 degrees of freedom. The area under the curve to the right of the cutoff is 1 minus 0.05, which is 0.95. So here again is our drawing. This is a left tail test, which means the 0.05 is the area of that left tail. But Table 8 is always asking for the area to the right. And so the leftover area on this right side would be 1 minus alpha, which is 0.95. Now that we have that information, we can go to Table 8, the chi-square distribution table. Here is 19 degrees of freedom. And up here we'll look for an area to the right of 0.95. So here's the 0.95. See where those line up. And it looks like they line up at 10.117. So 10.117, that is the cutoff for that left tail. The next thing to do is to calculate the test statistic. And the formula for the test statistic is this formula. Again, it's the ratio of the sample variance to the sample standard deviation. Note that sigma sub 0 is the population standard deviation of the null hypothesis. So in this case, sigma sub 0 is the 4.25. That was the standard deviation using the old sculpting technique. Remember also that the sample size was 20, and we calculated the sample standard deviation to be 3.13 millimeters. So we could put all of those numbers into the test statistic formula, and we'll get 10.3054. The last thing is to determine whether this test statistic is inside the critical tail or outside the critical tail. So the cutoff was 10.117, and our critical value is 10.3054. This is 0 on the very end of the chi-square distribution, and then it increases from here. So 10.3054 is right outside that tail. It's just to the right of 10.117. So for this study, our test statistic, 10.3054, is outside the critical tail of our curve, and therefore the results of our study are not unusual, and we would say that we do not reject the null hypothesis. In the next video, we'll take a look at the other approach to testing this hypothesis.